Today we're going to talk about another way that we can do um, the integral as net change. The College Board sometimes talks about it as being what they call an accumulation function. And that's kind of a good way to think about it also. But today we're going to look specifically at density. Now in physics, density is usually mass per unit volume, right? That's the only kind of density that you look at. But there's a whole bunch of other kinds of density. Like you could look at population density. Um, Sometimes if you look at various cities around the world, especially large cities, places like Tokyo, the population density there, number of people per square mile or whatever, is extremely large. You got a lot of people crammed into a very small area. Whereas if you were to look at, um, you know, the population density of the unincorporated of Houston area of Houston, that's going to be much less. You don't People tend to be much more spread out, which makes me happy. We can have concentration density, right? Um, One of the things that I think I told you guys, I may not have. My dad, before he died, was a wildlife biologist, specifically fisheries. And a lot of times, what you would be looking at, he would be taking water samples, and he was looking for the number of parts per million of a particular whatever it was that he was looking for in that sample of water. So the parts per million was the density of whatever it was. Um, in any of these cases, we can use the idea of multiplying the density and the volume or the area to find the total mass, population, or amount. So if you know the population density of a city is, I don't know, 1,000 people per acre, let's just say that, and you've got 5 acres, well, you just multiply the density times how many acres you have, and that gives you how many people you have in that area. That's the basic idea. So a common one is if you have a rod of length L, so think something like, a meter stick, right? And it has a linear mass density of, and that's not a P, that's the Greek letter rho, if I remembered my Greek letters correctly, grams per centimeter. Then the mass of the whole rod is the length of the whole rod times the density. If rho is not a constant, but a function of the distance from one end of the rod to the other, so think of perhaps this rod is thick on one end and gets thinner on the other end, right? Then what we can do to find the mass is take the integral from 0 to L of the density. Because what that's going to do is, remember that the definite integral is really cutting that up into a whole bunch of little slices. Well, that's what this is doing. This is cutting this up into a whole bunch of little slices and multiplying the density here by the thickness of that slice, dx, which is very, very, very small. Or if you think about Riemann sums where it was a little bigger, that's the basic idea. So find the total mass of a 2-meter rod of linear density. Rho of x is equal to 500 over 1 plus x squared grams per meter, where x is the distance from one end of the rod. Well, it couldn't be any more straightforward. That is simply the integral from 0 to 2 of 500 over 1 plus x squared dx. So most of these we'll use a calculator for. We may eventually on this one, but right now I'm going, yeah, okay. I can take the antiderivative of that. What is the antiderivative of that? I'll give you a hint. Factor out the 500 first.
Like a tangent inverse.
Yeah, that's exactly right. It's 500 times the tangent inverse of x. from 0 to 2. So that's 500 tangent inverse of 2 minus 500 tangent inverse of 0. And that's where the problem starts. Tangent inverse of 0 is no big deal. I know that that's 0 because tangent of 0 is 0. But tangent inverse of 2, I haven't the slightest idea. So that's where we'll grab a calculator. Comes out to be 553.574 grams. All right. So if the density is in units per area, what we're going to have to do is multiply the density times the area, where the area is the area of a strip or a ring, and I'll show you both of those. So here we've got a rectangular piece of land, shown in this diagram, that borders a straight piece of ocean beach. Okay. Yeah, we must have taken a picture or something because that doesn't actually happen. But like always in math, we're idealizing it. Okay. The salt concentration in the soil is given by the function f of x is equal to 10 e to the negative 0.5x grams per square meter, where x is the distance from the beach. Find the total amount of salt on the land. All right, so to help you kind of think about this, if we take what I call a representative slice of this, this distance is going to be 50, right? And this is going to be some little thin slice, and we're going to call it dx. So the area of that slice would be equal to 50 times dx, right? And the concentration, the amount of salt on that little slice would be, I would substitute whatever the x distance is from the beach, and then I could find for this slice how much salt was on it. So I just want to do that over and over again. So I'm going to have the integral from, what does x range from and to?
0 to 120.
0 to 120, exactly right. And we're going to have f of x, 10 e to the negative 0.5x, times the area, which is going to be 50 dx. So then we're just going to chuff that into the calculator. So the integral from 0 to 120. I'm just going to make that 500 because I can multiply those two together in my head. And we're taking the integral with respect to x. So there's 1,000 grams of salt on that. It's interesting that that came out so nicely. I don't remember where I stole that problem from. I didn't make it up. All right. So let's look at one more. And this is kind of an interesting question. So the population in a certain city has a density function, rho of r, which is equal to 15 over the square root of 1 plus r squared, where r is the distance from the center of the city in kilometers, and rho has units of thousands of people per square kilometer. So how many people live in a ring between 10 and 30 kilometers from the city center? So what's happening here is as you move in concentric circles away from the center, the population density becomes less. It's the greatest density is at the center of the city, and as you move further out towards the borders, the population density gets to be less. So what's going to happen is if I have the whole city or whatever, I'm going to draw this outside border. This is where we're 30 kilometers, and this is where we're 10 kilometers. So there's nothing in here in the middle. We've got this donut. The math word for that is a torus. And we've got, for our representative slice here, I'm going to have this really thin, and I can't draw this worth a darn on this. I draw it much better, believe it or not, on an actual piece of paper. So I've got this ring right here, right? Okay, so I know that this distance is 10, and this whole distance, I know, is it raining? What am I hearing? It's raining? Okay. I didn't know it was supposed to rain today. I'm actually more worried about next week. If you looked at next week's forecast for the middle of the week,
It's cold.
really cold and like a 60 to 70% chance of snow and freezing rain and that kind of stuff on Tuesday.
That would be kind of fun to do walking to school.
So yeah, I'm concerned about whether or not we will be here.
Online school. No.
So for this ring, you're like, well, how much area is inside of that ring? Well, think about straightening it out for just a second. If you straightened out this ring, this is going to be your dx, right? And what is this distance going to be?
30.
No.
Okay.
I've taken this circle and straightened it out.
It's
It's the
the circumference.
circumference, exactly right. And the circumference is going to be 2 times pi times r.
No.
So the area of this strip is 2 pi r times, actually this is going to be not dx but dr, right? A tiny little change in the radius. That makes sense. So if I take the integral of the density times the area, because this was in, I know it's got to be area because the units on my density is people per square kilometer, right? So I want to multiply the density times an area. So I'm going to have the integral from 10 to 30 of 15 over the square root of 1 plus r squared multiplied times the area of that strip, which is 2 times pi times r times dr. So, go to the calculator. I'm going to factor out to the 15 times 2 pi. You can do it inside or outside, it doesn't really matter. So I'm going to do 30 pi times the integral I'll be left with r over the square root of 1 plus r squared. Oh, hang on. Clear that. I did that totally wrong. Sorry, I thought I was into the integrand already. 30 pi. Math 9. From 10 to 30. I've got x over the square root of 1 plus x squared. Dx. So, and since this is people, I would probably go, all right, it's about 1,882 people. If you get questions like this on the AP exam, they will usually, to avoid any confusion, say, to the nearest person. That's a relatively big city with not a lot of people in it. Except I've done one thing wrong and I just noticed it. Why is my answer totally wrong?
Does it have to do with the units?
Yeah. What are the units on my density?
Square kilometer.
Nope. Has units of thousands of people per square kilometer.
It's not so small of a population.
So I need to go back to this and multiply it times 1,000. So 1,881,825.
A bit more people.
Yeah. This is a big city with a lot of people in it. All right. Any questions about that? Okay. I have a worksheet for you.